Over the years, installers of copper communications cable have developed a number of successful procedures and techniques to make their task easier. When dealing with fiber optic cable, however, new skills must be acquired to avoid damaging the optical fibers within the cable structure. Today's designers and installers must also address a host of changing building codes, environmental issues, proper design, routing, and topology concerns for installations using fiber optic cable. Let's examine these and other important issues involved with fiber optic cable placement. In our previous design video, we planned a fiber optic link between two office buildings. In this, like many such installations, a number of cable placement types are used. Plenum cable runs horizontally on each floor, interconnecting riser sections, users, and system electronics. Backbone cabling typically involves riser-rated cable being distributed from entrance facilities to the horizontal cross-connects located strategically on each floor. From building entrance facilities, interbuilding cable can be directly buried, placed in underground ducts, or may travel in raceways placed in corridors or steam tunnels between buildings. Depending on the design of your fiber transmission system, your cable installation requirements may include indoor, outdoor aerial, directly buried, specialty cable, or a combination of these. In many indoor situations, fiber cable will be installed in plenum areas, often above acoustic ceiling tiles or below raised computer flooring. Plenum areas allow for air movement in building ventilation, so national building codes are very strict as to the type of materials used in communication cable. Most of the codes are concerned with the cable's reaction to heat and the production of toxic smoke. Most countries have established national electric codes concerning indoor electrical construction. In certain situations, local regulations supersede national codes. Riser cable must be capable of withstanding the stresses of its own weight. The maximum vertical rise is the maximum length of cable that may be mounted vertically without strain relief. It is recommended that the cable be tied off at least every 2 floors to limit stresses due to cable weight. Always follow prescribed laws or building codes and keep accurate, as-built diagrams of the installation complete with footage markings on the cable to assist with future expansion or restoration efforts. Whatever the placement type, whatever the cable type, the 2 critical factors for a successful installation are cable bend radius and pulling tension. Exceeding manufacturer's specifications on either of these factors may damage or impair the quality of the optical fibers within the cable. Failure may not be immediate, but may show up days or even years later. Most cable installations are designed to provide 30 years of service, a lifetime obtainable only when proper installation techniques are employed using products designed for the application. This chart shows specifications for a breakout-style fiber cable. Note the ratings for bend radius and pulling tension. For this cable type, the manufacturer allows a minimum bend radius of 20 times the outer diameter of the cable when it is being handled, and 10 times the outer diameter under static conditions, such as slack storage. A dynamic tensile rating of up to 2,700 newtons, or 600 pounds, is allowed for short periods, such as during installation, but must be reduced to below 500 newtons, or 110 pounds, when installation is complete. To pull in a cable, a pulling line must be in place along the planned route. This line could be a nylon rope, mule tape, or even a pre-existing cable being vacated. It may be snaked through a plenum area or be fished through a duct or conduit. An efficient way to place pulling line in existing duct is by vacuum. A lightweight nylon cord is attached to a piston or mouse and is fed into one end of the duct. At the other end, a large shop-style vacuum cleaner is attached, which draws the piston and pulling line through the duct. This process works with empty ducts or with ducts containing existing cables. It can place several hundred feet of pulling line in a few minutes. Pistons of various sizes are commercially available, but a homemade mouse can be a quick alternative. The mouse is made from a small plastic bag that is taped to a small length of nylon hose. The hose allows the bag to inflate with air and provides a connection point for the pulling line. In order to effectively pull in a cable without damaging the fibers, you must identify the strength members of the cable and attach it to the pulling line. Several methods of attachment can be used depending on the cable structure. With direct attachment, the cable strength member is tied directly to the pulling fixture. If aramid yarn is present, it can be used for direct attachment or provide added grip with indirect attachment methods. Fiberglass epoxy rods may be secured to the pulling fixture with tight clamping plates or screws. If the cable has a central steel strength member, a small length of it may be formed into a pulling eye and attached to the pulling line. With indirect attachment, pulling forces are distributed over the outer jacket of the cable structure. If strength members such as aramid yarn are located beneath the jacket, a minimal amount of stress will be transferred to the fibers. A common type of pulling fixture in use is the Kellam's grip. It is reliable for cables as small as 0.6 centimeters in diameter, all the way up to the largest diameter fiber cables in use today. The grip is chosen to match the cable characteristics and will spread pulling forces over a 1/2 to 1 meter length of cable. When the grip is in place, it is usually covered with electrical tape to reduce friction during pulling. A swivel should be added to the pulling line to prevent the cable from twisting. Because of the concentration of stresses where the cable attaches to the pulling line, after the cable is installed, the first 3 meters of cable should be cut off and discarded. When pulling a very small diameter cable through short runs, the cable itself may be tied to the pulling line and covered with electrical tape to prevent the joint from hanging up along the span. The electrical tape is applied from the cable end towards the pulling line so the tape edges overlap like fish scales. This prevents the tape edges from snagging during the pull. The tape also seals the cable ends, preventing fiber damage and contamination by dust or moisture. During any cable installation procedure, care must be taken to properly seal the cable ends. For short-distance installations, mechanical pulling equipment and lubrication are usually not required. When pulling cable by hand, remember to apply even tension rather than a series of sharp tugs on the cable. For cable installed in exposed cable trays or raceways, it may simply be laid in place or pulled through ducts installed in the raceway. As with all installations, bend radius is a critical factor. Cable clamps or tie wraps can be used to prevent cable movement, especially at corners. However, the cable must not be crimped or squeezed too tightly and must be protected from sharp edges. When passing from one raceway to another, or when the cable must leave the raceway, a small section of split duct can be placed over the bend and tie-wrapped to a secure fixture to maintain correct bend radius and provide added protection. The use of ducts containing pre-installed pulling rope offers maximum protection for fiber optic cables and ensures the cable will not snag in the raceway during installation. The choice of pre-installed pulling line is cost-effective because it costs less than if purchased and installed separately. A fast and efficient method of indoor fiber installation is the use of air-blown fiber, or ABF. A cable similar to inner duct containing a number of small plastic tubes is first installed along the planned route. Because the tube cable does not contain any fiber at this point, pulling tension and bend radius concerns are not as stringent, allowing easy and quick installation. The number of tubes in the cable will depend on the present and future application of the system. Junction boxes are used to interconnect the tubes of various cables using small push-fit connectors. This method eliminates much of the splicing and connectorization involved in complex fiber runs. When all the junctions have been made, compressed air carries a bundle of fibers through the tube cable past each junction to its final destination. Air pressure pushes the fiber bundle through the tubing, while a jet of air is passed through the tube ahead of the bundle to allow it to float on a cushion of air, eliminating the friction present in conventional pulling. Because there is no external pulling tension applied to the fibers, installation stresses are reduced to near zero. Fiber lengths of up to 2 kilometers can be installed using this technique. As easily as the fibers are installed, they can also be ejected from the tube cable for quick replacement by blowing in the opposite direction. The air-blown system provides fiber on demand for applications involving many adds, moves, and changes. When working in buildings, it is best to work from the top down, since vertical cable pathways tend to become more congested on the lower floors. By pulling cable down from the top floors, it will be exposed to less friction during the majority of the pull. On each floor, a generous amount of slack cable is looped at the correct bend radius and stored for use in the cross-connect panel. Because the exact location of the cross-connect may not be known during cable installation, always leave more cable than you think necessary. The cable is dressed and mounted along with an appropriate amount of slack, with any excess cable pulled down to the floor below, where the process is repeated. By leaving adequate slack during cable installation, you can eliminate unpleasant surprises later in system construction. When cables must pass through walls, building and safety codes dictate that they must pass through conduit. A quick and efficient way to comply with these codes uses this commercially available sleeve that is pounded through the wall. On each side of the wall, a washer and clamp secures the sleeve in place. A split sleeve is also available that is designed to install around existing cables passing through walls, thus bringing the installations up to code. Wherever cables, ducts, or conduits pass through barriers, such as floors or walls, fire-stopping material must be used to plug up any openings. This can be done with foams, putties, or other sealants to form an airtight, fire-retardant barrier. Horizontal cable is routed from cross-connect panels to individual users. This can be done through plenums or by the use of undercarpet fiber optic cable. Horizontal cabling can also connect the riser section with the building entrance facility. Entrance facilities are required by electrical codes as a transition from indoor rated cable to the outdoor styles used in inter-building applications. Outdoor cable installation can be underground or aerial. Underground cable can be plowed in, installed in underground ducts, placed in trenches, or placed by trenchless technology. In this example, a remote building on a campus must be connected with fiber optic cable. A system of underground ducts and manholes is present on the campus, but no ducts connect the remote building. A small trenching machine is used to open a trench from the building to a site near a manhole where the ducts have been exposed. The desired duct is tapped and a conduit installed in the trench to the remote building. During the installation, a pulling line is fished through each section of a conduit as it is placed in the trench or blown through the completed duct. A reel of fiber optic cable located at a manhole near the center of the fiber span feeds cable into the manhole towards the existing hub. The fiber distance from the manhole to the buildings is calculated, leaving plenty of excess cable for slack, and that amount is reeled off and placed in a figure-8 pattern on the ground. This technique protects the cable from excessive bend radius and twisting. The end of the cable is then connected to the newly installed pulling line and pulled through to the remote building. The cable must be protected from vehicular and pedestrian traffic while on the ground. The successful installation of underground cable depends upon careful route planning and engineering. As pointed out in our design video, a route survey addresses environmental issues, identifies all conflicts and obstructions, right-of-way access points, and repeater locations if required. The survey will also investigate soil conditions along the route to define the appropriate cable type, suitable installation methods, and depth of burial. Construction codes such as EIA, TIA 590 specify burial depths of 45 to 75 centimeters depending on the application of the cable. However, in harsh climates such as in Alaska or Western Canada, fiber optic cable should be placed at least 1.8 meters down, well below the frost line. If trenching is selected as the placement technique, the grade of the trench bottom must be determined. If the ground is reasonably level, the trench should drain in both directions from the center at a rate of 7.5 centimeters per 30 meters. The depth of the trench must provide for the minimum cover required and must be wide enough for the conduit formation plus a working space for construction. The sides of the trench, especially in loose or fluid soils, should be sloped. Where the trench is deeper than 1.5 meters, shoring safeguards are required. At the bottom of the trench, a 7.5 centimeter depth of fine sand or dirt should be placed prior to laying the conduit, duct, or cable. In marshy or unstable areas, a 7.5 centimeter slab of concrete can be poured to provide a stable base. In urban areas, or wherever added protection is needed from dig-up or crush forces, concrete can be poured over the duct structure as well. For long-haul runs, it may be cost-effective to directly plow the cable underground. Plowing saves time, manpower, and money whenever long distances are involved. However, even when plowing, a certain amount of trenching or other cable placement types may be needed to bypass obstacles. Duct, fiber optic cable, or cable in conduit can be placed underground by cable plows for long-haul applications. Standard plowing equipment is most often used, but modifications may be required to meet the cable manufacturer's specifications. Plows can be mounted on rail cars when installing cable along existing rail right-of-ways. This also provides a convenient method of transporting additional cable reels. When plowing over open land, depth of burial will impact the type of equipment used. For shallow installations under 1 meter, a single cable plow is usually sufficient. Deep installations below 1 meter, or areas of very hard soils, often require the use of an additional caterpillar to provide increased traction. During cable installation, a dynamometer should be used for continuous monitoring of cable tension. Variations in cable tension are caused by startup, uneven terrain, speed changes, and unexpected obstacles, and can easily rise to unacceptable levels. Armored fiber optic cable is most often placed directly underground by plowing, but the possibility of cable damage can be reduced by either plowing in duct first and installing cable later, or installing cable in duct in a single operation. In either case, tension on the cable is significantly reduced when duct is used. The added protection offered by the duct allows the use of armored or unarmored cables in these spans. In this desert installation, the soil is as hard as rock and requires pre-ripping prior to installation. When rocky areas are encountered, rock chippers move in to break a path for the pre-ripping operation. Only then can a cable plow safely install the cable or duct. When plowing duct, a joint may not necessarily correspond with a fiber optic cable splice point. In these cases, a duct coupler connects duct sections and is buried. At fiber splice points, an underground vault or above-ground pedestal should be placed to house the splice closure. At least 15 meters of cable should be left here to allow splicers to work in splicing vehicles or tents. Slack cable is also important for future expansion or restoration efforts. The excess cable can be coiled, secured, and properly racked with the splice closure. Manholes are common forms of splice vaults and are most often precast from high-strength concrete with bonded reinforcing steel. The steel is then bonded to the wall inserts, which grounds the racking equipment. If the fiber optic cable includes metallic strength members or armor, these must be properly grounded to the manhole racking. If not, lethal electric charges could build up along the cable runs. Smaller cable vaults are often made from plastic composites. They are cost-effective, lightweight, and easy to install. They too may require special grounding techniques when used with cables containing metallic members. Pulling cable through long sections of underground duct will require mechanical pulling equipment and lubrication. Curves, turns, and undulations in duct placement will determine the amount of friction encountered during the pull. It is important to use the correct duct type for your application. Corrugated duct is flexible but would offer too much friction for long pulls. In smooth wall duct, a large surface area of cable jacket contacts the duct wall, resulting in high friction. Rib ducts reduce this surface contact area to a series of edges, significantly reducing friction. Wherever ducts are present, their open ends invite the possibility of contamination. A number of reusable duct plugs are available to combat this problem. Using compressible rubber seals, duct plugs can be fitted to empty duct or to ducts containing cables, effectively sealing out dirt, moisture, insects, and rodents. Lubrication will be needed on most long pulls. Many ducts are available as pre-lubricated, and specialty lubricants appropriate for pulling fiber optic cable are available from a number of manufacturers. These lubricants are usually water-based materials with soluble high polymers, which make them slippery. Some contain silicon oils or microspheres that act like tiny ball bearings to reduce friction. For long pulls, it is important that the lubricant completely coats the cable jacket and stays on the cable through the length of the run. When choosing a lubricant, remember that it must be compatible with the cable jacket, duct materials, installation method, and must be rated for the ambient temperature during installation. Some cable manufacturers maintain lists of appropriate lubricants for use with their cables. In addition, sets of pulling equations or user-friendly software is available to calculate tensions and lubrication parameters for your installation. Lubricant manufacturers provide application equipment ranging from hand pumps and T-style applicators to various styles of lubrication saddles to make the job clean, easy, and efficient. Center pulling of fiber optic cable is recommended for long-distance runs. From the midpoint of the span, the cable is pulled from the reel in one direction. After pulling through an amount of slack cable, the remaining cable is spooled off the reel onto a figure-8 pattern on the ground. The cable is then pulled in the other direction to the end of the span. An alternative to center pulling is mid-span assist, where powered winches deliver pulling force to the cable at periodic points along the span, rather than at one point. This eliminates the need for figure-8ing the cable on the ground, thus saving time, labor, and the possibility of cable damage. The winches have built-in tension monitoring, allowing them to balance pulling force along the cable route. New technology is having a significant impact on fiber optic cable installation. High airspeed, air-blown cable installation is becoming very popular with many installers. It operates in a similar manner to the air-blown fiber system we looked at earlier, but with entire cables as opposed to small fiber bundles. A large capacity air compressor is set up at the blowing head location. The fiber optic cable passes through a set of hydraulic-powered tracks that pushes the cable into the blowing head and into the duct system. High-pressure air enters the blowing head and is directed coaxially along the cable into the duct. This creates a high-velocity airstream that drags the cable through the duct. The drag forces are distributed along the entire length of the cable, eliminating the tensile forces concentrated at one end of the cable during conventional pulls. The distributed force on the cable is just high enough to overcome friction and is so small that the cable can easily be stopped by holding it with one hand. As a result, fiber stresses are reduced to near zero during installation. Because of zero pulling force, there is no need for large or steel tension members to be present in the cable, allowing the use of smaller, lighter, and less expensive cable types, and no pulling ropes in the ducts. This system is also independent of duct loops, curves, and undulations that would hamper conventional pulling. The hydraulic pusher is required to overcome the local resistance of the blowing head and its internal seals, and does not push the cable through the duct. It also acts as the controlling device for starting, stopping, and regulating cable speed. Other technologies that are making cable installations easier include directional boring. Obstacles in the cable route, such as rivers, highways, and railroad tracks, can create significant problems. Disrupting an interstate freeway to place a cable would be very expensive, if even possible. In many applications, environmental concerns and difficult permit processes make open cutting a poor choice. In built-up and landscaped areas such as residential neighborhoods, trenchless cable placement is indispensable. Directional boring makes use of a steerable tunneling device that can travel under, around, and between obstacles and other utilities without any surface disruption. Two small pits are excavated, one on either side of the obstacles to be traversed. The drilling equipment is positioned at the starting pit and the tool head sent on its way. In this example, the cutting head uses high-pressure liquefied clay to cut through the soil as a drill pipe pushes it forward. More sections of drill pipe are added to advance the cutting head. The position and depth of the tool are constantly monitored by highly accurate locating electronics. Crew members keep in radio contact to control the depth and direction of the cutting head to keep it on track to avoid obstacles. When the cutting head reaches its target, the steerable head is removed and replaced with a reamer. The cable, duct, or conduit is attached to the reamer using a swivel, and the drill pipe drawn back through the tunnel, completing the operation. For longer spans, larger boring equipment is used to place high-density polyethylene or steel casing through which duct or cable can be pulled. Aerial placement of fiber optic cable may be an attractive alternative to underground placement, especially when existing right-of-ways and aerial structures are already in place. Although the EMI immunity of fiber optic cable allows its placement almost anywhere on a utility pole, it is usually placed in the communications or free space below the phase conductors of power lines. In many cases, a metal messenger must be installed first, with the fiber optic cable or duct lashed to the messenger. Alternatives to metal messengers include figure 8, ADSS or OPGW cable types. For new installations, it is generally not cost-effective to install messenger followed by cable in separate operations. Rather, it is better to use a self-supporting or figure 8 cable, saving an installation step. In the figure 8 style, the fiber cable contains its own integral messenger, allowing it to be attached directly using standard pole and tower hardware. The all-dielectric self-supporting, or ADSS type, also requires no messenger and can be used in spans of up to 3,000 feet. Because it is all dielectric, it finds extensive use on or near high-voltage towers. Optical power ground wire, or OPGW, is designed to be used as a static line for attracting lightning on utility towers. To be effective, OPGW is placed as the highest conductor on the aerial structure. Some installations make use of OPGW as the neutral conductor as well. The most important concerns with aerial cable placement are span length, cable tension, and cable sag. Cable sag and tension will be determined by the maximum span length and cable type to be used. Sag will also depend on the minimum required ground clearance at the center of the span. This must also take into account the effects of wind and ice loading throughout the year, as well as cable expansion and contraction with ambient temperature changes. Keep in mind that sag and tension are inversely proportional. The more tension, the less sag. Cable sag will often be affected by aesthetic concerns, such as matching the sag of other cables on the aerial structure. It is also important to note that the coefficient of thermal expansion of fiber optic cable is not as great as that of metal cables, so sag variations due to temperature will not be as severe with fiber optic cable. Cable tension must be adjusted to keep sag within specifications year-round. Because optical cables are lightweight, adjusting cable sag may be more difficult than with heavier cables. Lightweight cables may also display undesirable effects in windy conditions. Drift, galloping, and vibrations can often cause cable and hardware damage if not remedied. The use of airflow spoilers, vibration dampers, and center span weights can reduce the damaging effects of bad weather. An efficient way of installing self-supporting cables is the backpull method. The cable reel is placed on a reel stand or trailer at a stationary location. Here, a tensioner is placed in line with the cable reel and aerial structures. Cable clamping hardware is installed to the structure at the appropriate height, and travelers placed just above or below the desired framing location of each support structure. A small pulling line is then run through the travelers at each aerial structure and attached through a swivel to the cable. The cable is then pulled through the section while carefully monitoring pulling tension. At the end of the cable reel or the end of the route, enough slack is left for splicing. The messenger or cable must be dead-ended at the start of the cable run or where direction changes are made. Dead ends are available in a number of styles, from bolted clamping devices to automatic compression types. Another type of dead end uses a wrapped grip that works similar to a Kellam's pulling grip. When crossing roads or freeways, each side of the span should be dead-ended to minimize the possibility of a downed cable. At pole or tower locations, the cable or messenger is attached to the structure using 3 bolt clamps or wrapped grips. When the line is straight or changes angle less than 6 degrees, the 3-bolt clamp method is most widely used. For line angles of between 6 and 25 degrees, armor grip supports are the preferred choice. These grips consist of a strain relief placed around the cable to which a series of twisted interlocking rods are added. The rods are center marked for correct alignment and are snapped into place sequentially over the strain relief and cable. When complete, a clamp is secured over the center of the grip and attached to the pole or tower. When using ADSS cable, special clamps are used to gently grip the cable with compressible rubber inserts. When the pole is very close to trees, or if there are conduits running up the pole, it may be necessary to mount the cable clamp on an extension arm to give the required clearance. At this point, the cable is not yet securely fastened to the pole to allow for tensioning. Installation continues until a number of spans have been installed. Usually, tensioning is done from a pole where head guys have been installed to provide firm support. Depending on the cable type and application, you may use block and tackle, chain hoists, or tensioning jacks to apply tension up to 20 spans at a time. Most specifications call for tensions ranging from 1,500 to 3,000 pounds. After the correct amount of tension has been applied, the cable is firmly clamped at pole locations. In lashed installations, a lashing machine is used to bind the cable securely to the messenger using steel or nylon lashing wire. The machine is pulled along the span by a person on the ground. At pole locations, the lasher is simply removed, passed around the pole, and reattached so the process can continue. The lashing wire is securely anchored at pole locations. When using cable lashing, the drive-off installation method tends to be faster than pull-ins. The first end of the cable is clamped at a pole and to the messenger using conventional hardware. The lasher is attached, the lashing wire anchored, and the lasher pulled along. Fiber optic cable is fed from a reel positioned on a truck that moves ahead of the lasher. In applications where high voltages are nearby, it is best to use an all-dielectric self-supporting cable to eliminate damage and safety hazards caused by induction. However, where this is not possible, metal messengers must be grounded periodically along the route, usually at 3 points per kilometer. Another critical point that is often overlooked is proper grounding of streetlights in close proximity to communication cables. Safety codes usually mandate that every light within 100 centimeters of a communication cable must be bonded to ground to reduce the possibility of personal injury should a craftsperson contact an energized streetlight case and grounded cable messenger. The installation of OPGW cable is similar to the placement of conventional ground wire. However, even though OPGW provides excellent protection for the optical fibers, bend radius, pull tension, and twisting must be carefully controlled during installation. The hardware and accessories used with OPGW have been specially designed to avoid damaging the optical fibers. Conventional cable hardware should never be used. Splicing is the primary difference between OPGW and conventional ground wire. Splices should be located at poles or towers with enough slack stored at the correct bend radius. The splice closure should be placed high enough to discourage vandalism, but still within safe reach of restoration crews. One innovative aerial installation technique for utility use is wrap-over phase. It is used as an alternative to OPGW on structures that already incorporate a static line. Fiber optic cable is wrapped around the ground line or even a phase conductor, eliminating the need for a lashing operation. Because the cable is all dielectric, lightning strikes are unlikely to damage it. To install wrap-over phase cable, a cable reel is mounted to a wrapping machine which is pulled along the conductor by a remote-controlled tugger or pulling line. After powering down the transmission lines, the equipment is first hoisted into position over the conductor using a small boom and pulleys. To place a section of cable, 2 machines are sent out from a starting tower called the spin point. One half the cable is paid out in each direction. When the machines reach towers along the route, a carryover is performed where the machines are carried over the tower and reattached to the conductor. If the next tower is reached when the cable reel is nearly empty, the cable is fed down the tower so a splice point can be made. When calculating which towers along the route will be used as spin points, 5% of the total cable length on the reels must be allowed for wrapping, slack cable for splicing, and cable sag. With any type of aerial installation, the following considerations should be kept in mind. Fiber optic cables should be clearly marked periodically along the route. At pole locations, a drip loop should be employed to allow water drainage off the cable. When working near energized power lines, be aware of the safety hazards posed by induction and flashover. Be especially careful to remain outside the minimum approach distances as outlined in National Electric Safety Codes. Even though fiber optic cables may be all dielectric, a static charge can build up on the cable's surface when close to high voltages. Water evaporating from the cable surface will leave conductive residues that encourage scintillation, a surface arcing that can damage cable and cause injuries. Scintillation mainly occurs near cable attachment points and can be reduced by proper bonding to ground at regular intervals along the route. Clean, dry cable has the highest surface resistance, while wet cable can reduce resistance by up to 60%. For this reason, never install cable on active towers during wet weather. Whatever type of installation method is chosen, safety must always be your top priority. Be sure to follow the guidelines laid out in all pertinent construction and safety codes. Whatever equipment is used during installation, be sure to fully understand its operation and safety requirements. As stated earlier, a well-designed fiber system makes installation as easy and cost-effective as possible. Unexpected changes in the field are difficult, expensive, and may result in an unreliable fiber system. Only through careful installation can you ensure that the fiber cable will deliver top performance over the design life of the fiber system.